This video will detail bioenergetics.
Oh, when the sun beats down and burns the tar up on the roof, and your shoes get so hot you wish your tired feet were fireproof. Under the boardwalk, down by the sea, yeah.
Bioenergetics is very important because without free energy, or the energy derived from different breaking of bonds or different chemical reactions in our body, we couldn't survive. And so one of the things that's very important in bioenergetics is obviously delta G, so Gibbs free energy with this little knot. So delta G knot. This knot talks about standard states. So standard states are those things where the elements are most stable, right? 1 atmosphere pressure, 25 degrees Celsius, room temperature. The products and the reactants of all the equations are at 1 molar. So what we can do and what we're going to do is in biochemistry we add a little bit of modification, and that's where we say the concentration of H plus is 1 times 10 to the negative 7, which would give you a pH of 7, which would be biological pH. And so what we call this is delta G naught prime. And so delta G naught prime, that prime just tells us these reactions, or these reactions are at standard states where you have 1 times 10 to the negative 7th pH. One of the things that we're going to do is we can calculate delta G naught prime, or delta G naught, of a reaction. And to do that, it's the sum of the delta G of the formation of the products minus the sum of the delta G naught of formation of the reactants. We'll go into more detail in this in class, but that's how we get delta G naught prime of a reaction. When we calculate this, and we see a number that is at least minus 4 kcal per mole, so minus 4 or less, we know, I won't show you how we know, but we know that the equilibrium constant of this is equal to 10 to the third. And what that means is that this reaction will go to 99.9% completion. And so not only will that reaction be very spontaneous, it will pretty much be 100% complete. So let's look at another example of delta G and what it can tell us. And so if delta G naught prime of the reaction is in between so it's at least minus 2.7 kcals per mole, so that would be in between minus 2.7 and minus 4. K equation, or the equilibrium constant, is equal to 100. When that happens, then this reaction is not only spontaneous, but it'll go to 99% completion. And so that's very, very important. And so we know that when delta G is calculated, if it's negative, it's spontaneous, and it will usually go to completion. If it's positive, it won't normally happen. So let's look at an example of us combining a couple of different equations to make a favorable delta G. So let's look at CO2. So we have to kind of remember back to our general chemistry days and Hess's law that states we can combine two different reactions together, and then we would calculate or add in Hess's law it's enthalpy. Here we'll talk about Gibbs free energy. And so here is a reaction that occurs in our blood through carbonic anhydrase. The delta G of this reaction is equal to positive 0.8 kcal per mole. Ran out of space there. So it's 0.8 kcals per mole, but it's positive, right? It's not going to naturally occur spontaneously. So what we can do is we can couple it to a different reaction. So here's another reaction. Oxaloacetate minus 2 plus hydrogen goes to CO2 plus pyruvate minus 1. The delta G naught prime of this reaction is minus 7.4 kcals per mole. So not only does this oxaloacetate turning into pyruvate occur, it occurs spontaneously, and it pretty much goes to 100% completion. And so if we remember what Hess's law tells us, whenever you have products or reactants that are the same on opposite sides of the equation, so let's look at an example. So let's look at CO2. CO2 on this equation is a reactant, on this equation it is a product. When that happens, these will then cancel out. And now we have hydrogens canceling out. And so what we're left off with is oxaloacetate minus 2 plus water goes to bicarbonate plus pyruvate. So when we do this, when we combine these two equations, we can also combine their delta G's. And so when we add these two together, the delta G naught prime of this reaction is equal to minus 6.6 kcal per mole. And so this is obviously delta G naught, right? So it's standard states. We'll see this. One of the things that we can couple with some equations that might not be favorable through Gibbs free energy is adding ATP, the energy currency, to these reactions to help us overcome some of the constraints on a reaction. And so we'll look at that more in class. So one of the things I do want to let you guys know, and I'll just do it on this slide, is that not everything in our body is standard state, right? We don't have 1 molar concentrations of glucose in our body. If we did, we would die. So there has to be a correction for non-standard state conditions. And so here's the correction. And so we have an equation that's in equilibrium. And so we know what we can do is the equilibrium constant, so KEQ, is equal to C to the C power, D to the D power, whoops, sorry, that's a lowercase d, A to the A, and B to the B. And so what we can do when we're trying to calculate delta G of the reaction, right, because delta G is what we want in non-standard state, what our bodies would be normally doing, is delta G naught prime of the reaction plus RT, temperature with which it occurs. R is constant, is a constant. The ln of C to the C, D to the D, A to the A, B to the B. And so what this is this is known as Q, the mass action ratio. And so the mass action ratio is Q. Now, in the case when we get to, let's say our reactions in our body reach equilibrium, right? So at equilibrium, what's going to happen? Well, delta G naught of the delta G of the reaction is 0 at equilibrium. So when that's the case, delta G naught prime of the reaction is equal to negative RT ln of the equilibrium constant, right? Because we're at equilibrium. So in living biological systems, we don't ever want to officially reach equilibrium, because we don't want our Q here to equal KEQ there. And the reason why we don't want to do that is for a variety of reasons. One of the reasons is if we reach equilibrium, then the push of things through metabolism is no longer there. And so our metabolism will stall out. And so the last thing I want to cover, so that's just a brief overview on bioenergetics. We'll cover it more in class, a little bit more in detail. Whether I'm here or not, we'll do that. But the last thing I want to do before we shut this video down is I want to show you guys, or to help you guys with a little bit more of an organic chemistry review, because this is going to be very important as we enter into metabolism and we start seeing some of these concepts. So let's talk about let's define some terms real quick. So nucleophile and electrophile. So a nucleophile are groups that are capable of donating electrons. Right? These are groups that donate electrons. Usually you will find nucleophiles with lone pairs. Electrophiles are groups that seek electrons. Usually because they're electron deficient. Right? And so a nucleophile donates electrons. That will be attacking, as I've said in class. Electrophiles will be the attacked thing, and they seek electrons because usually they're electron deficient. So some of these electrophiles are things with a double bond. So one of the best electrophiles we'll talk about, and that we'll commonly see in these next few chapters, are carbonyl groups. Carbonyl groups are very important groups for a variety of reasons. One, they're good electrophiles because you have a partially negative charge and a partially positive and a partially negative charge, so you have a dipole moment. That allows the nucleophile then to attack that carbon. They can hydrogen bond, right? So this oxygen has the ability to hydrogen bond. This oxygen also has the ability to stabilize metals for catalytic activity, right? So carbonyl groups are very important in these different types of situations. There's other things that we can do to make something a good electrophile or a nucleophile. We activate it by either removing a proton or adding a proton. There's a variety of different things that we can do. So let's talk about a few different types of reactions. The first type of reaction that we're going to talk about is aldol reactions. You will not, so for the exam number 2, you will not be required to draw the mechanism of these reactions out. But you are required to, if I were to give you a real life example of these mechanisms, to actually recognize what type of mechanism it is. So, aldol reaction. Here we have our organic compound. Now, these R groups can be the same. I'm just putting in just R's just to show you that they might be different. So, what happens? How does this work? So, how this works is we activate this carbon. Let's change color so we can see. We activate this carbon by removing a proton, right? We said we can activate things to be good nucleophiles or electrophiles by either adding or removing protons. So we remove a proton. We now have a carbanion. That's not good. And so it is a great nucleophile. So what happens is this nucleophile attacks this carbonyl group. What ends up happening is now that carbon is bonded to 5 things. We can't have that. We break this double bond, and this double bond goes and picks off an oxygen or a hydrogen, usually the one that is pulled off this carbon. And so what we get, I'll do it back in red, is this. And so there's the aldol reaction. And so these R groups can be really anything. They don't have to be carbon. So that's all aldol reactions. So let's look at an example of what's known as a retroaldol reaction. So retroaldol, retro just means reverse. So this would be a reverse aldol reaction. And so here we have a compound. I'm just going to be lazy and draw phosphate like that. We have an OH. We have an OH. We have an H. O. H. And what we're going to see, what we're going to focus on is this. We're going to focus on that, right? Because that's in between those hydroxyls is where this is going to work. And where we see this is in glycolysis. So this molecule that I just drew is fructose 1,6-bisphosphate or diphosphate. You see it in both ways. So the enzyme that does this is aldolase. And so what you see is that aldolase uses a base, a general base. It'll remove that proton. It'll form the double bond between that oxygen. But like we saw before, 5 things will be bound to this carbon. So what will happen is these electrons will come and pull off that hydrogen from the base, right? Because we have to regenerate the enzyme. And we get 2 different products. I'll draw them in green. We get 2 different products. We get this. I'll actually draw this in red so we can see where it came from. CH2OH, right? Because we put that extra hydrogen from the base for the reaction, plus And I'll again draw this one in red to see where that came from. Right? And so this is an aldol reaction just in reverse. And so this is known as a retroaldol reaction. This is DHAP. And this is glyceraldehyde 3-phosphate. Now we'll talk more about these when we get closer to glycolysis. There's another one that we can talk about, and this is Claisen ester condensation. So if it's a condensation, then we bring two things together, and so this will be seen in the citric acid cycle. So we have acetyl-CoA. And what we do with acetyl-CoA is like what we did before, is we activate it through the removal of a hydrogen. We're going to add it to something we've seen before. Bond S, bond R2. So what's going to happen is, like what we saw before, this is going to attack. Let's change colors to see it. So those electrons, that nucleophile is going to attack that electrophile. Electrons come up. Now instead of the oxygen pulling off the proton like what we saw before, we're going to see a cycle down just because sulfur is a really, really good leaving group. So this sulfur is going to leave, pick up the extra proton, and what we get is this. Right? And this is actually, when we talk about citrate and citrate synthesis and the citric acid cycle, this is the kind of condensation that is performed. And so now let's look at things that can happen within a molecule. So this is decarboxylation of a beta keto acid. So we'll see a lot of this in the citric acid cycle, beta keto acids. And so what is a beta keto acid? So we have this. So this looks very similar to the product we formed in the last with the Claisen. So those are all electrons. So let's count, or let's name these carbons. This would be your alpha carbon. This would be your beta carbon. So decarboxylation of the beta keto acid. So what happens is this lone pair comes down, forms the double bond. It'll break off from the beta carbon. Those electrons will pick up a proton, and I apologize. Let's do this again in a different color. Those electrons flow down. These electrons will come and pick up a proton, and what we're left with is this. We are left with a carbon chain that is down one carbon because we have emitted CO2. We have broke off as CO2. And those things just happen naturally. And so what we'll see is, we'll see this in more detail when we talk about the citric acid cycle. The last final type of chemical reaction that we're going to talk about dealing with organic chemistry is what's known as internal redox reactions. So we're going to look at glucose 6-phosphate. So this is the second step in glycolysis, going to fructose 6-phosphate. And what we're going to see is the enzyme that performs this reaction is an isomerase. So remember, it doesn't change any of the molecules in the compound, it just changes the way they're bound. So we're going to zoom into the actual place where this takes place. I'm not going to write the whole molecule. So glucose 6-phosphate. So this would be an H because it's an aldehyde sugar. So what's going to happen is in the isomerase we have activated, we'll just say that's base 2, we have activated a base. We gave a proton to it. What's going to happen is this carbonyl is going to grab that proton. We're going to regenerate that base. And so we have a little bit of a transition state. So there's two different bases. This base has been protonated, so we remove that proton from that carbonyl group. This base removes that proton, causing a double bond to form in between the carbons. And so what we get is this. So we need to generate the way these looked, and the way they looked before was base 1 did not have a proton attached to it, whereas base 2 did. So now we have to regenerate it. So we're going to take this and we're going to remove that proton, those electrons, back to the base. And what this base is going to do is going to remove that proton, causing these electrons to float down to the bond to make a carbonyl group. So what we get is this. So what we have effectively done is we have changed this carbonyl group and we moved it over one spot. So we just did a flip-flop. We regenerate the base, right? So the base 2 has a proton, base 1 does not have a proton. And so this is just an internal redox reaction. This is what isomerases do. Remember, we can tell what things are either reduced or oxidized based on how many oxygens they are bound to.